think. Okay, I'll just reproduce it. Yes, it's easier. So we had this integral that we wanted to maximize. In fact, that integral was equal to pi, and the integral itself looked like this. Go from 1 to alpha of 1 minus omega over 1 minus omega squared x squared to 1/2 dx equals 0. So the idea was to look at this function as a function of omega and minimize it. That would maximize the alpha. So when you do this, which you did correctly, set it to 0 and solve for omega, you get a very simple function. You get that omega equals 1 over x squared. Okay, so you got this far, right? And then you didn't continue, but it's actually not that hard. So again, if you're only interested in finding the maximum alpha, then you don't really need to look into what trajectory this actually describes. Because remember, this is some kind of unitless omega. It's and x is some kind of unitless radius. So it's not immediately obvious what this trajectory is. So I'll first explain how to find alpha, because this is the ultimate question of the problem. And then I'll also give you some tips as to how to convert this to the actual trajectory. So in order to find the alpha, what you really need to do is simply plug this back into the integral and integrate. Okay, that's pretty much it. And then you'll have two integrals, right? If you distribute the numerator, you'll have two integrals. So let me write both. First one is integral from 1 alpha 1 over, no, it's the second one, dx over 1 minus omega. And if you substitute omega already, you get this, right? So omega squared is 1 over x to the 4th times x squared gives you this. So this is the first integral to compute. And the second integral is integral from 1 to alpha minus 1 over x squared 1 minus, same thing, x squared to 1/2 dx. Okay, I know it's not a physics, it's a calculus exercise, but I feel that it may be helpful for you. Or you could probably just tell me how to do these integrals, and that would be it. So folks, have you dealt with integrals like this? It's a yes or no question. Hit a thumb up if you have, and clap if you haven't. Okay. Well, yeah, I know you've been taught these magic words in calculus, but they're like not really informative. U substitution doesn't tell me anything unless you tell me what U is. So yeah, both of these integrals can be computed using a substitution. In fact, the second one is easier to do because you can recognize that 1 minus 1 over x squared dx is simply d of 1 over x. Guys, can you hear me okay? Is the background noise not too bad? Okay. Okay. Yeah, I'm not sure what Euler substitution is, but yeah. So this is the sub you do in B, and then this is that thing squared. You have one integral, and I may call it U, I may not call it U. It's not really going to make a big difference. So d of 1 over x divided by 1 over minus 1 over x squared. So this is a arc sine integral, right? So arc sine of 1 over x with the substitution from 1 to alpha. So it's arc sine of 1 over alpha. Sure if we can read it okay. 1 over alpha. Minus arc sine of 1, which is pi over 2. Okay. So this is the second integral. In the first integral, you want to do some massaging first. So you write alpha. You basically factor out 1 over x from here, and that goes on top. It becomes x dx over 1 over root x squared minus 1. Does that make sense? Okay, and then again, you combine this as 1/2 d of x squared, and you got x squared on the bottom, so it becomes square root of squared minus 1 with the substitution actually yeah, pretty much it. Okay. Who add to pi? Oh, the two integrals? Yes, the two integrals add to pi. Okay, anyhow, this is simply square root of alpha squared minus 1. And then exactly, you use that final condition that, pi equals a plus b. So you get pi equals square root of alpha squared minus 1 plus arc sine of 1 over alpha minus pi over 2. So of course you can combine the pi's, right? Carry this over, but other than that, there isn't much you can do. So this is what I meant by saying transcendental. So let me just do it right away. 3 pi over 2. So this is the Beast equation. This is where your analytic stops. Like there is no way to solve this equation for alpha explicitly. So this is where people stop and just solve it numerically. The easiest thing for you to do if you have a graphing calculator is just graph this thing, right, and see when it crosses 3 pi over 2. Right? Or whatever other software or apps you use for graphing, just graph this function and see when it's equal 3 pi over 2. Does that make sense? And if you do this, actually, you know what? Let me not give you the answer. Why don't you do it? Okay, and tell me next time what you got. Okay. So this is certainly greater than pi plus 1 that we discussed early on in this process, but not super much greater numerically. Yeah, so somewhere in your sophomore and junior year, you may be able, you may be seeing equations like this. Like when you like deal with like a mix of functions that are not mixable, and there is no regular way to solve equations like this. Okay, any questions about this part? I know I went pretty quickly about the integrals, but I hope you can insert the missing steps here. Okay, now the other piece about the trajectory, so you basically have to come back to one of those individual integrals, specifically the one for the student. So let me go back to that. Yeah, so you remember where this came from. So you basically need to substitute omega in one of these integrals. Okay, integrate, because that gives you how the radius depends on the angle. Okay, and this is what we'll describe a trajectory: the actual radius r versus the actual radius theta. Okay, and as I said, it would be a very simple trajectory once you do that. Well, Leon, that's one way to solve this equation approximately. But I have to tell you that alpha is not well, actually 1 over alpha is fairly small. It may work fine. You could try doing that. You still need to deal with the square root. So let me just check. Folks, is it clear how to get the actual trajectory? So if you look back at this note where we derive the angle, say student angle covered over the whole trip. So you set that equal, you substitute what you found for dimensionless omega and this omega as well, and that gives you the trajectory. Okay. The integral itself is again an arc sine, so it's fairly straightforward to do. But yeah, if you go back to that transcendental equation, yeah, you can assume that 1 over alpha is small. Like do one of those tricks that we did with the dropping a block on a spring problem, where we made an assumption that the answer is smaller than something, so you can actually approximate some functions, and then see if the actual solution is consistent with that original assumption. If it is, then you good. But if it isn't, then that assumption is not really accurate. Okay. So again, I'm not exactly sure if that will help. If you can, of course, assume that 1 over alpha is small, remove the arc sine and just have 1 over alpha, and you still have the square root. So it's still a nasty equation to work with. So again, or you can try to expand it. That may work. Like if you factor out alpha squared out of the square root, I'm just trying to play along. So if you rewrite this as alpha times 1 minus 1 over alpha squared, right? And then assuming that 1 over alpha is small, can approximate it, as you probably remember. So folks, you remember how to approximate these things? You have 1 plus x to power n. For x much smaller than 1, this is approximately 1 plus nx, okay? So power n is 1/2 here, and x is negative 1 over alpha squared. So it's 1 minus 1 over 2 alpha squared. So again, doesn't seem to be helping. You'd probably be dealing with a cubic equation, or maybe not. So anyhow, Leon, this is your suggestion. So hopefully this additional tip helps. Maybe. So go ahead. I wish you good luck here. Okay, so well, let's just get back to more recent stuff. And talk about some of the homework problems. Yeah, so let me just tell you right away. In question 1 and 4, you will need to understand momentum conservation. The other questions don't require that. Okay. So, but I did want to briefly give you some hints on some of these problems. So I'm actually, maybe we'll, yeah, let's do that. So let me give you a hint on number 2. So have you guys given it a thought at all? I didn't see any submission. So can somebody just describe like what will be happening to this ball on the hoop? Like qualitatively, just explain in general words what will be happening. I realize that this may require knowledge of torque and angular momentum, but just for the sake of qualitative argument. No deep knowledge. So Joseph, you're actually on the right track. It won't actually just fall straight down. Well, it will in the beginning. So think about it. There is, like, because the hoop is massless, the ball will just really drop down, straight down, until where? Yeah, of course we do. Yeah. Folks, in case you didn't catch, so there was a question in the chat if we're assuming that the hoop is perfectly balanced in the z dimension. Yes. Don't worry about that. Yeah, so if you think of the torque, you will soon realize that it won't really turn the hoop. So the torques all have to be balanced on the hoop. Let me actually tell you this. Since we're talking about torque, if you consider the ball as your possible axis of rotation, then the torque on the ball itself is 0, but the hoop is massless. So the torque on the hoop has to be balanced. For the same reason we argued that a massless string cannot have a non-balanced net force, right? If you think about F net equals MA, M is 0, even if A isn't, okay? So the net force has to be 0 for any massless object. So the same thing here. So Joseph is really correct as far as the first part of the process. So the ball will fall down, but it won't actually get to the floor. It will get to this bottom point. Okay, and then it will be it will be a hit through the hoop by the walls, like the wall on the floor. So let me just say this. So the impact will be absolutely elastic. That means whatever vertical velocity how do I say that? So basically, the ball's velocity will just reflect whatever the vertical velocity was. It will become horizontal by symmetry. Am I making sense? And after that, it's purely projectile motion because, again, the hoop is massless. It's not going to affect anything. So basically, the hoop plays a role only momentarily during the bounce, but at no other point in time. So first, the ball just simply free falling until the symmetric point, and then whatever velocity it's picked up bounces and becomes horizontal. And then you have projectile motion. And you need to find the distance between this point and this point. That's pretty straightforward. So just do Pythagorean theorem. You know this height right away, right? And this distance you can find from projectile motion and this speed here. Whatever speed it picks up at this point, you just make it horizontal. And that allows you to figure out everything about this projectile part. Does that make sense? Yeah, so with this idea, I should be able to finish this problem. Any questions? Okay, now, let me, okay, let me maybe comment on number one as well. And we'll study momentum right now, but there are two approaches to this problem. And in one approach, I want you to recognize that the ball on which this the ball on which the small block is sitting won't rotate. Do you see why? Let me draw this situation. So you have a little block that starts sliding. It is frictionless, but it's partially the reason. You're right. That's a necessary condition, but not yet sufficient. So if you consider the center of the ball, it like when would this rotate? It would rotate if there is a torque around the center, right? You can say torques are balanced, but you can actually make it a little bit stronger. You can say all torques are actually zero. Think about it. The force from the surface is passing through the center of the ball, obviously cannot exert any torque. So friction could, you're right, friction could create a torque, but it's zero. Gravity and normal force, they are passing through the center of the ball. They cannot create this torque. And then the last force, the force from the block, it's a normal force, right? But it's also passing through the center. So that creates zero torque as well. So what will be happening to the ball as the block is sliding, it will just move sideways without spinning. Does that make sense? So if you realize that, the problem doesn't look as bad. You don't need to consider rotational motion. Okay. Okay, so well, let's quickly recap momentum and then we'll maybe make a few more comments on this homework. Yeah, I know almost everybody is familiar with momentum pretty well, so let me just do it real quick. So first, momentum is defined as m times v, and this is a vector quantity. So in general, it's a three-dimensional thing. In fact, Newton stated his second law not in the form that you may have gotten used to, F equals ma, but actually in this form. He said the time derivative of momentum equals the net force acting on the particle. So this what Newton called second law of motion. In fact, you can interpret this philosophically as the definition of force, right? Not some statement, but actually what is a force? Force is the rate of change of momentum. So let's see, when is this consistent with the other definition or the other statement of Newton's second law that you got used to? So if you take this time derivative, d dt of mv, and assume that the mass is constant, then you immediately get. So let me actually not assume that mass. Yeah, thanks, Alvin. Exactly. So let me allow mass to change. If mass is allowed to change, then you have to do the product rule and write this: dm dt times v plus m dv dt. And this is exactly the ma term, right? But this is a new thing. So this is a new thing that has to do with the mass rate change. And again, this is not zero if mass changes. And you probably know what systems work, like their principle is based on the fact that mass is changing. What am I talking about? Rocket, exactly. So think rocket. Did you guys, are you guys familiar with the rocket equation? Like if you start out with some amount of fuel, burn it, to what speed will you accelerate the rocket? Okay, very good. So let's then transition to momentum balance equation that we'll need to use for solving problem. So you consider a system of particles, system of point particles. Each of these particles has a momentum, P1, P2, and so on, Pn. Then you can talk about the total system's momentum that I'll denote with capital P. This is the sum of the individual momenta, 1 to n. Yeah. So total momentum. And then see what may change the total system's momentum. So let's consider the time derivative of this guy. And here, let's assume that mass is a constant. Like mi's are constant for every I. Okay? Then you basically need to take derivative of each individual momentum. This term will drop out. You will have m1a1 plus m2a2 plus so on m-a-n. Excuse me, a second. Yeah, so you already recognize that we can replace it with f net 1. This is f net 2. And this is f net n. But now think about this. These forces, they come from two parts, internal and external. So internal is from the other particles in the system, another n-1 particles. And external are from external agents that are not in the system. So internal and external. So tell me what happens if you add all internal forces. So how many do we have? Let's say we have 100 particles. That means each internal force is like 99 forces, right? F2 on one plus F3 on one plus so on Fn on one. Like 99 forces. And then for this guy, you also have 99 forces. And that's for everything. So you have like 9,900 forces. Uh-huh. Who is Niels Wang? Okay. Yes, you're right. So all these internal forces add to 0. And that's okay. And that's really neat because that means that internal forces don't really change the momentum of the system. So what you got is this. The change in total system's momentum is simply equal to F net external. So total external force. And no mention of internal forces. So for momentum balance equation, I'd like to rewrite it momentum balance equation. I like to rewrite that in a format that resembles the energy balance equation. So I'd like to approximate the time derivative as delta P over delta T. And then I can write delta P as F net external times delta T. Okay, so this is what we'll call momentum balance equation. So I just want to highlight some important similarities and differences with the energy balance equation. So for energy, we had this. Delta E equal work done by non-conservative forces plus work done by, external. I suspect that in some literature this may be called that. Yes. So what's on the right hand side is the impulse of the force. So in that sense, you may say, yeah, impulse of the force equals change in the system's momentum. But it's important to understand like that this is just the external force. If you again that's what I want to discuss like real careful here. So if you compare with the energy, you have two terms here, right? But in this equation, you only have one. So you don't have the non-conservative part. Non-conservative forces are not treated in any special way when it comes to momentum. I want you to recognize that. For example, if you have internal friction, it would spoil conservation of the system's energy, but it won't spoil this conservation of system's momentum. Is that clear? But let's just do a quick example. Oh, and a couple other things real quick. So this is a scalar equation. Energy is a scalar thing. It doesn't have a direction to it. Momentum does. So if you're in 2 or 3D, this is actually 2 or 3 equations to consider. Okay? So let's just do a quick example, real simple. Call it dog and log problem. So let's say you have a log on a frictionless floor. So this is the dog. runs and jumps on the log. And let's say the dog is running with some original velocity v. The log is stationary. Okay. Say given the mass of the dog M1 is 10 kilograms. The mass of the log is 30 kilograms. The initial velocity of the dog, which I just call v, say 20 meters per second. So you understand what's going to happen, right? That the dog does, and then they slide together with the dog, with the log, right? So I want to find that final common velocity. But before we do this, which is really simple to do, tell me, do you expect the mechanical energy to be conserved in this problem? No is the right answer. Yes. Again, you can say so just intuitively, because whenever the dog does this, it's a sound. But more importantly, there is also friction involved. And as you know, friction would spoil conservation of energy. Plus, there is, of course, some sound energy that's got emitted away. So how do we set it up? Strategy is actually very similar to the energy strategy. Let me just quickly type it up. Same 3 steps. Well, not exactly the same, but very similar 3 steps. That's the strategy you will basically follow in any momentum related scenario. So first you identify your system, decide what's in the system, what's not. And then you consider the right-hand side of the momentum balance equation. See if it's under your control. Ideally, want it to be 0, okay? And we'll discuss in general when it may be 0, or more importantly, negligible. And once that's established, you do the left-hand side of momentum balance equation. When I say do, I mean expand the left-hand side, because in terms of all the individual momenta, final and initial, and then do the math. So this is, again, very similar to what we have for energy. I suspect many of you already got the answer, but let me just quickly follow the strategy. The system is the dog and the log. Then we'll look at the right-hand side of the momentum balance equation. What is it? We need to look at the external forces. What forces are external here? Is that it? Joseph, what do you think? Well, here is my point. You guys don't need to be thinking on questions like this. I mean, it should be in your spine by now. So external forces. So I got gravity listed. What else? Leon, Vincent, do you want to help? Yeah, but that doesn't answer my question. What do you mean you don't have paper? Not taking notes? Didn't I tell you taking notes by hand helps a lot in, learning the material? There is a connection between your right hand and your left brain. Anyhow, folks, I'm not going to torture you anymore. That's just the normal force from the floor on the log. Okay, frictions are there between the dog and the log, but they're not external. And this is the key. Okay. Now, these forces are there, but they're vertical, right? They're not horizontal. And that means that they really don't affect the horizontal part of the motion. Besides, they cancel each other out. Okay. So you can say this is zero. Okay, zero vector. That means you can proceed and establish that obviously the left-hand side must be zero as well. Okay. And folks, I urge you to actually do the first two steps, because it's not always that you have the zero. So you have to first recognize that. Otherwise, you cannot really apply momentum conservation because it may not be conserved. So anyhow, it is conserved for us. Can rewrite it as P initial equals P final, and then just expand the initial momentum of the system, the final momentum of the system, and you can just focus on the x-axis, which I'm going to choose in the standard way, x. All right, so when you project on the x-axis, what is P initial? Initial momentum is only the momentum of the dog. So it's m1v. Okay, with plus zero, just to emphasize that the log's initial momentum is zero. And then at the end, you have the dog with the final velocity and the log with the final velocity, which you can, of course, rewrite as m1 plus m2 times v final. They move with same velocity. And then you can solve for v final. That is just v times m1 over m1 plus m2. Okay, so this is the answer. Happens all the time when objects stick together after the collision. Jumping ahead, we'll call such a collision absolutely inelastic, when the maximum possible amount of energy is lost. So numerically, you probably already computed this. This is 5 meters per second. Okay, any questions? Now, I have a question for you folks. Just do it at home. Let me maybe type it here. Compute K total initial, K total final, and find the ratio. So what is your feel for it? What do you expect this ratio to be? Less than 1, greater than 1, equal 1? Okay, very good. So you have a decent expectation here. Now you know everything you need to know. Just compute total, initial, final energies, find the ratio. And that will explicitly show that energy is not conserved. So, okay. So, actually, it's a good time to make a pause. And after that, we'll consider elastic collisions. So let's take a 10-minute break. We have another Leon. Yep, Alvin, you're right. Okay, so I'll see you in 10 minutes. The collision is elastic. Okay, find the final. So I know you know the answer, but let me just show you how that follows from the equation. So collision being elastic means that kinetic energy initial equals kinetic energy final. Right, so that means 1/2 mv initial squared equals 1/2 mv final squared. And what does that give you for the final? Oh, putting things in the chat. Yeah, thank you, Alvin. Very, very importantly, it gives you plus minus, not just one sign. And indeed, you pick the minus. You pick a negative solution because the ball goes in the opposite direction. Okay, very good. Let's remember this result. Here is the next problem. And this is actually what I really want you to take home. Suppose, actually, I'm going to use the same picture. I'll just use a different color. The wall is now going to the left with some given velocity u. How many of you know this problem? Oh, we did? Sorry. Thanks. Okay, but did you get the answer? Trying to remember. I mean, not to this one. Yeah, okay then. Good. So thanks for reminding. So then you know that the final equals what? Looks like we didn't do it. Yeah. Okay, yes, this is it. So yes, very good. So it's negative v plus 2u. And this factor of 2 is actually very non-intuitive at first. So just keep that in mind. And the technique is something that you'll be using a lot. And even on this homework, that's a good technique. But going forward, it will also be pretty helpful. So let me just remind you the strategy. And you can, and it looks like we did it already in detail. So just look back. So the strategy is this: switch to the walls frame. Yeah, that will give you v initial prime. Well, we'll call everything in the walls frame prime. Then do the collision still in the walls frame, so that will give you the final prime. And then, of course, we need to switch back. Switch back to the lab frame. And that'll give us the final without the prime. Right? And let me quickly insert the steps. V1 prime is V plus U, right? From if you sit on the wall, you think the ball is going to you faster. So V plus U would be the parent speed. When you do the collision, you simply get a negative sign. So you get minus V plus U. And when you switch back, you need to actually take this away, right? Subtract U to go back. So that gets you an extra U. Subtract it, minus V minus to your plus if you put it in parentheses. So this is roughly how this works. And I'll ask you to use the same approach on another homework problem that I'll assign after we're finished with the collisions. Tell me if everything is good so far. Any questions? Okay. So example number 3. So it's a really good use of your big textbook. So think of a, say, ping pong ball or tennis ball that you put on the table, and then consider this textbook that you move with the velocity u, and the ball is originally stationary. So again, you do your best to ensure that the book moves with the constant velocity u. What do you think will happen after the book hits the ball?
We're assuming that the mass of the book is a lot more than the mass of the ball, right?
Yep.
Okay, yeah. So then, since we can just use like the last one, except v is 0, so then the ball goes at a speed of like 2u.
Okay, what do you folks think? I want everybody to either say something or put something in the chat. Joseph, Leon, Vincent, what do you think? So the book keeps going with velocity u. It's totally unaffected. Okay. Yes, folks, this is correct. So v final equals 2u. And yes, you can kind of immediately get it from the previous question if you put v to 0 and realize the fact that the wall is now moving the opposite direction it was in this example. So you don't need the minus. So indeed. So I encourage you to do this experiment at home. You won't be able to tell that the ball is going twice the speed of the book. It's hard, right? But at least you would see that the ball is going faster than the book, because like when I ask this question to random people who had not seen the previous example, they attempted to say, oh, the ball will just pick up the speed of the wall. But no, if that was the case, they would be moving together, right? The ball would appear stuck to the book. It doesn't really happen. The ball obviously takes over and moves faster than the book, and specifically twice as fast. Okay. Does anybody play soccer? So think of this situation. The ball is rolling towards you. And well, Joseph, you can now start playing theoretical soccer. So the ball is rolling towards you and you want to stop it. Of course, there are many techniques, but your particular technique now as a theoretical soccer player is to move your foot backwards. say given v is 20 meters per second, you want to move your foot backwards so that when the ball touches your foot, it actually stops. Visualize that. It's not just theory, it actually works in reality, but how fast do you need to move your foot backwards? Such that the final is 0. Yes, exactly. Joseph, I expected an answer from you too. So yes, indeed, the u has to be half the ball speed, just 10 meters per second in this case. So yeah, in general, when you think of sports like tennis, ping pong, when you move your paddle or racket forward, you get extra double speed of the racket to the ball. But if you move it backward, you actually subtract the double speed of the racket, the foot, the paddle, whatnot. Okay. Finally, let's start a new page. Does anybody play pool? Okay. Yes, Newton's cradle is based on this. But we'll focus on one dimension. We'll be able to do two-dimensional situations a bit later. Okay, so first off, what is so special about pool balls? They're identical. I mean, good pool balls have identical mass. And in fact, we can just call it M. V, and let's call this one 1. This is ball 2. V2 initial is 0. At home, I'll ask you to do a general situation when V2 is not 0 but given. And this is V1 initial, but for simplicity, I'll just call it V. So V1 initial is V. V2 initial is 0. Okay. I want to find V final 1 and V final 2. So we know everything before the collision. We want to find what happens after the collision. And I bet you know the answer, don't you? From your playing experience. Okay, got something from Leon. Joseph, very good. Yes, so great. So you know the answer. Now we'll see how that follows from physics and math. So we expect, and yeah, we have a head-on collision, of course. If it's not head-on, this is indeed two-dimensional, as Alvin said. Head-on collision. So we expect that V1 final is 0. The first ball stops, and the second ball actually gets exactly the speed of the first ball and just continues on. Are you doing this in your lab? I understand it's a virtual lab, but is this what you're considering right now in your classes? Okay, so then we'll just be real quick here. So this is a perfectly elastic collision, which again for us means that energy is conserved and momentum is conserved. So let's write both equations. Momentum conservation tells us what? The initial momentum is just the momentum of the first ball. So this is m1 v, and again, I'm skipping the subscripts on the one initial, so I'm just putting it as v. So m1 v plus 0, just again emphasizing the fact that the second ball has 0 momentum in the beginning, equals m2, sorry, m1 v1 final plus m2 v2 final. Okay, and then the same with energy, kinetic energy to be specific. So we put 1/2 m1 v squared plus 0 equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So folks, we have two unknowns, v1 final and v2 final, and we have two equations. So math-wise, that means we're good to go, and we can solve this stuff. So let me call this equation 1 and this equation 2. You may wonder, why have I put distinct masses in here if they're equal? Well, for the reason that will be clear a bit later. Let me do this. Let me divide each equation by m1. And I want to introduce this quantity, alpha, the mass ratio, which is given by m2 over m1. So note that it's 2 over 1, and that means stationary over the incoming ball. And we'll consider all possible reasonable alphas later on. So if I divide everything in the first equation by m1, the equation 1 becomes v equals v1 final plus alpha v2 final. And equation 2 becomes, if you also cancel the halves, you get v squared equal v1 final squared plus alpha v2 final squared. Looks nicer, right? So I want you to remember these equations, because one of your future homework problems will be based on these two equations. But now I'm going to set alpha equal to 1 as is given, and see what happens. And equation 1 becomes v equals v1 final plus v2 final, and v squared equals v1 final squared plus v2 final squared. So, of course, there are many ways to solve these equations. Probably the most efficient one is to square the first equation and then subtract equation 2 from it. Equation 1 squared gives you what? Gives you v squared equals v1 final squared plus v2 final squared plus 2v1 final v2 final, right? Just expanding the square. And if you subtract equation 2 from it, then what do you get? So tell me, what do I get? Exactly. So I get that V1, or yeah, I can put 2 for now, V1 final times V2 final equals 0, which means that one of these guys is 0. So let's consider both situations. V1 final equals 0, or V2 final equals. So what happens if this is 0? Then you can use equation 1 again, and that gives you V2 final equals V. In here, that will give you V1 final equal V. So let's look at both answers and see which one is relevant. So what do you think, folks? Okay, yeah, this is obviously the solution that agrees with your intuition. Okay, so we'll call this solution the hit solution. But look at this solution. Mathematically, this is perfectly fine, right? So this solution has an interpretation too. Do you see that? Probably never happens to Leon, but to somebody who is a novice in Pole, may happen. What situation does this describe? Yep, exactly. So we'll call this the miss solution. When the first ball simply misses the second one, so it just keeps moving, right? V1 stays the same. Second ball just not moving at all. So keep that in mind. Remember, whenever you write the energy equation, kinetic energy equation, it's a quadratic equation in general. So it should not surprise you that you get two solutions to it, or two solutions to any system that involves a quadratic equation. And oftentimes you actually can give a meaning to both of these solutions, not just the one you're really interested in. Okay? So let's go back. To this general situation, and not require that alpha is equal to 1. Just assume some general alpha and solve these equations. Okay? Oops. So assume general alpha. So if you do the same, like square equation 1, what do you get? So let's look back. So you square equation 1, you see this extra alpha in here? So that will show up. So the equation will read v squared equals v1 final squared plus alpha squared v2 final squared plus 2v1, actually put alpha first, to alpha v1 final v2 final, right? Now, if we subtract equation 2 from it, what do we get? So again, let's look back. The left-hand sides cancel, right? 1 squared minus 2 gives us 0. So let me put it in here. 0 equals. What else do we have? We have v1 final squared and alpha, just one alpha, not alpha squared, v2 final squared. So You subtract, these guys cancel, you get a 0 in here. Then you have alpha squared V2 final squared minus just alpha that, V2 final squared. And of course you have this cross term, it doesn't go anywhere. To alpha V1 final, V2 final. Look at this. This can be simplified, right? We can cancel some factors. What factors? Okay, very good. You can cancel one factor of alpha, here, and one factor of V2 final. So let's rewrite this equation. 0 equal V2 final, alpha times that, minus, actually, let me factor it out. V2 final times alpha minus 1 plus 2 V1 final. Okay. So from here, we get V1 final. For example, you can eliminate, right? You can write that V1 final equals V2 final times 1 minus alpha over 2. And then you can substitute it in equation 1 back here, right? Do some massaging and get the answer. So why don't you guys take a minute or two, compute this, and tell me what the answer is. This will be a very important result for us. It will show up in a lot of places. Oh, can you express it in terms of alpha? Almost. We'll double check the numerator. Oh, wait. I think you're overthinking. So Joseph, Leon, Vincent, what do you think? Oh, Leon, do you still not have paper? Okay, that works. Yes, Alvin, but you can simplify. Oh, I see now. Okay, yes, but yeah, why don't you simplify? Because it looks like what you put in terms of the m's is already simplified. You know, it should be consistent with whatever you do with lambda alpha. Okay, got the first answer. Very good. Here is the deal. I'm going to write it down, and the other guys, you test if Alvin's answer makes sense or not. Okay, so what Alvin got for V1 final is this. It's a V times 1 minus alpha over 1 plus alpha. Do you have V2 final yet? So guys, you start testing it. So what do I mean by this? Write down this equation, this expression. Okay, it's very easy to remember. V times 1 minus alpha over 1 plus alpha. Oh, and Alvin now has the second one. That's V times 2 over 1 plus alpha. So, folks, I want everybody to test this answer. So let's go back here. The first situation without the u, u0, okay? Do you see how these two problems are related? What would be the alpha? Okay, I want two more people to be engaged. Okay, I have a second answer. Leon, you would be right, but for a different example. So alpha is defined as stationary over incoming. Okay, so if we have a wall hitting on a ball, then yes, alpha is infinity here. And if we have the wall hitting the ball, that's when alpha is 0. Okay, so let's write it. So check using limiting cases. First, example 1, that is wall, sorry, the other way around, ball, the wall. That corresponds to lambda alpha equal infinity. Then let me label these equations star and put them in a red box. So what do these equations apply? If alpha is infinity, what happens to V1 final? What is it? Are you sure? Alpha goes to infinity. Right? So folks, you see, you can ignore the ones then, they're much smaller than alpha. And you have a -1 in here, so you get negative V. And what happens to the 2, the second velocity? Yep. Okay. Good. So we say equations star imply that V1 final equals negative V. V2 final equals 0. Is this consistent with the result of example 1? Looks like it is, right? Okay, good. So I put a fat check mark. Now let's consider, what was it? Example number 3. When you have a stationary ball that's hit by a wall. Then Leon is right, alpha is 0 for that situation. And equation star implies what? Just put alpha to 0 everywhere. Looks like V1 final equals V, V2 final equals 2V. Okay, so equation star implies V1 final equals V, V2 final equals 2. Okay, let's just make sure we understand it correctly. So 1 is now the wall, right? So that means the wall just keeps moving with the same velocity as it was. The ball moves with the double speed. Okay? That's exactly what we had, as you remember, right? So this is exactly right. And finally, example number 5, with 2 identical pool balls. Alpha is obviously 1. So let's check if you put alpha equal to 1 in these equations, then indeed you get 0 V1 and V2 final simply equal V. And exactly as we got. So this equation implies that V1 final equals 0, V2 final equals V, and this is also a check mark. Okay. Finally, let me ask you a new question. just intuitively, if alpha is greater than 1, like say, again, car accident, don't do it at home, a light car hits a truck. What happens to the car? Like a moving car hits a truck. Which way does it go after the collision? Backwards. Make sense to everybody? Yeah, so that means V1 final is actually negative. However, if it's the other way around, exactly, Alan. So if you look back at the equation, alpha is greater than 1, so this is negative. Now, the other way around, if alpha is less than 1, that means you have a heavier object hitting a stationary lighter object. That like heavy object just keeps going in the same direction. Doesn't bounce back. Does that make sense? So I suspect that sometime from now, you may not remember these exact formulas, but I hope you remember these 4 situations, okay? And if you vaguely remember what these formulas should look like, you can actually fix that by using those limiting cases, okay? So, and by the way, again, this equation star shows up a lot. Like whenever you have elastic collision, head-on collision, like it's there. So let me just give you another homework question. Consider general elastic collision. That is V1 initial is not 0 and V2 initial is not 0, and they're given. So these are the 2 givens now. You need to find V1 final and V2 final. So both objects are moving before the collision. You may want to assume that V2 is positive if the ball is going toward, like to the left in this case. Okay. So think of a neat trick. You may do it by brute force. Yeah. Yes, Alvin. This is the idea. Yeah. This is the neat way to solve it. But of course, you don't have to. You can just go back to the momentum and energy equations. Just do the math, but I don't recommend that. Do the nice trick to solve it. Let me give you one more question too, and we still have a few minutes. Just probably want you to recognize a couple important things. So this is actually a problem from a Russian Olympiad time ago. So this is a smooth rod, and you have a hollow cylinder that can slide without friction along the rod. The rod is fixed. It's fixed and it's horizontal, and this cylinder can slide freely. To a cylinder, you have a pendulum attached. And originally, it's actually horizontal. At the end of the pendulum is a heavy bob. Such that it has the same mass as the cylinder. So this is mass M and this is mass M. There is no friction anywhere. I can even give you the length of the rod. So imagine you let the rod go. So you understand what's going to be happening, right? The ball will start swinging, but then the cylinder will start sliding to the left. Do you see that? Because of momentum conservation, right? The original X momentum is 0. They both start moving. That means, you know, the momentum has to stay 0 at all times. So that requires both of these guys to move. And then at some point, actually redraw, at some point you have the rod vertical, momentarily vertical. So it's still swinging and the cylinder is sliding. So what I want you to do is to find the tension the force from the rod on the ball at the bottom. Given M, L, G, whatever you need, okay? Find the tension when the ball is passing the lowest point. Is everything clear? So you'll have to use like 4 or 5 different topics that we've discussed so far. It's like a capstone problem for you. Worth 20 points. So start thinking about it. We'll probably touch. So just to make it clear, the homework that's currently on, that's the one due on Thursday or Wednesday night rather, okay? But the problems I gave you today, Wednesday night is a soft deadline for them, okay? Sunday night is the hard deadline. Make sense? So, but again, try to do it by Wednesday night so that, you know, if you get stuck, I can give you a hint. Or if you just did it, then you're good. Okay, any questions? No? Okay, then let's call it a day. I'll see you on Monday. Oh, sorry, Thursday.